Hello, programming languages students. Welcome into another video here where we're going to talk about Prolog. This video in particular is a really good example of one thing that we're going to be doing a lot of, which is recursive method calls. And we'll talk about why they're useful, how they're useful, and some potential dangers and quirks about how Prolog actually runs that could cause you some trouble as we go forward. So this is a really good video to pay close attention to. So to start, we're going to have a database that builds child associations. So Bridget is a child of Anna, Caroline is a child of Bridget, Donna is a child of Caroline, Emily is a child of Donna. So again, we're following that sort of A, B, C, D, E pattern here. And in addition, instead of doing, so before we've done a previous example with father and grandfather, now we're doing child and descendant. Now the trick and the difference between descendant and grandfather is that descend, checking for descendants, could potentially go infinite, right? So if you have grandfather is only it's 2 generations, or I guess two, whatever. You have a child and your child has a child, you're their grandfather. With descendant, we could go many generations depending on how we set this up. Potentially infinite, right? And infinite cycles of infinite generations would lead to a descendant of yours. And so we set this up. We say that a child, we have an x and a y is a descendant of x if they're a child, or in this case we have another descend, which is x comma y, where if we have a child z of x and a child y of z, then y is a descendant of x, right? So if Anna has a child Bridget, Anna were x, Bridget is z, then Bridget as z has a child Caroline as y. That means that Caroline, our y, is a descendant of Anna, our x. So this allows us to go an extra generation. And so if we do a couple queries here, we could check for descend Anna, comma, Bridget, which should be true, and it is. And we'll talk about why this true and then false pops up because it's an interesting part of the discussion. Anna and then Bridget, and then Anna and then Caroline. Oops, Caroline is also true. And note that this runs once. This does not have, this one has true false. Descend Anna Bridget has a true and a false. Descend Anna Caroline has a true, and that's it. So real quickly, let's think about the decision tree. So we talked about decision trees earlier. The way that the decision tree works is it works its way down the list. So when we do descend Anna Bridget, we're going to look in our database, find the first descend that has 2 values, x and y, and we're going to check it. So we're going to check descend x comma y is child x comma y. And so descend Anna Bridget means that x is Anna, y is Bridget. So therefore all it's checking for is do we have a child, Anna comma Bridget? And we do. So that's where we get our first true. Now the reason we had a little wait and we had more things to search is that there's another descend. And so we had checked one descend and found it to be true, but we had one other descend to check with Anna and Bridget. And so the second thing we checked was this descend. This one, Anna is x and Bridget is y, checks for this specific relationship, child x comma z and child z comma y. So we checked child Anna comma and then z, and so that would have checked all the possible children of Anna, which is Bridget. And so we would have ended up with x is Anna, z is Bridget, and so to make this true, we would also need a child of Bridget and Bridget, right? Because y also has to be Bridget. And so this did not come out to be true. There's no child Bridget, right? So that's why we get a false. We got a true first for this, and then a false because we tried to check all the other remaining descend combinations and none of them worked. So the order here matters. The order that we place these statements matters. For example, let's say I switched this, and I descend xz child zy, and then descend xy child xy. Let's go back to our Anna Bridget comparison here. Let me get rid of Anna Caroline. Let's stick with Anna Bridget. If we run it this way, we get true and stop. So just by changing the order, we can get either true and keep searching or true and stop. And that's because the first thing that we find is true is this statement. So if we place it after the first one, we'll first evaluate this. This will be false. And so Prolog will keep running. And then it will evaluate this, which is true. And so in this order, we get one true statement and we're done. We've now checked all the possible descend combinations. In the other order, we check the first one, which is true, and there's still more to check, right? So every time that Prolog finds a true statement, it will backtrack and try to see if there are other options to get us to true. And so it backtracks and tries to check this option. So the order actually changes our output. So that's the first thing that's interesting. And we'll talk about how the order ends up mattering as we do recursive especially. Now, let's get back to the bigger problem. The descendant, we can check Anna and Caroline. Whoops, Caroline. Which is true, right? We covered this. But we would also like to see that Donna is also a descendant of Anna, which doesn't work here. So how could we make that happen? Well, we could add descend xy of child xz, and then in the middle we need a different child z comma, I don't know, u, and then child u comma y. So we've added an extra generation in here, right? So child xz, so child Anna Bridget, child zu, child z is now Bridget Caroline, u is Caroline, so we need a child Caroline Donna. And this now works. But if we want descendants to work forever, I mean, for our data set, we could add one more layer here and it would work. But if we want it to work for any possible set of descendants, there's no way to do it other than recursively. So let's take a look into the possible recursive, the possible recursive options here. So let's start with this. Let's change this to a recursive call. So we have descend xy if child xz and descend zy. First of all, I want to show you that this runs and it says true and then false. So we now have a recursive call. So we're trying to do descend Anna Donna. Let's see what happens. So we have descend Anna Donna. We find this descend method first, and this says that we are descendant if child x comma y is true. Right, that's the easiest descendant case. This is sort of our base case. Y is a descendant of x if y is a child of x. That's as simple as it gets. So with Anna and Donna, the first thing we check is this. Well, Donna is not a child of Anna, so this is false, and so we check the next one. So checking the next one, we start with child x comma z. So x, in this case, has to be Anna, and y in this case has to be Donna. So we check for child of Anna, and we look for all the combinations. So the first one we find is child Anna Bridget. So therefore we have assigned z to be Bridget. Let me leave some comments here. So we have child, we have descend, how about this, descend x comma y was our start here. We've assigned x to Anna and y to Donna. And that's if child Anna and z. Well, the only thing that makes this true is if z is Bridget. So z equals Bridget. All right, so the next thing we do is we have our next set of descendants. So now we descend with z comma y. Well, z must be Bridget because we have unified those in our previous iteration. And then y must be Donna. So we're going to check descend with Bridget and Donna. So let's go to our next line. We're checking descend with Bridget and Donna. So the first thing we check is descend x comma y child x comma y. So Bridget and Donna are what we're checking for our descend here. So we're assigning x equals Bridget in this iteration. And note, there's a separation here because this is another iteration. So Bridget is x in this iteration, and Donna is y. So we have Bridget descending from Donna. First of all, there's no child relationship here, right? Bridget and Donna don't have a child relationship, so this descend does not work. So we're going to check our next descend. So let me tab this over because we're still going to be in the same series here. So we're going to try descend with Bridget and Donna. X is Bridget, Y is Donna. And so we have to check child first. So child X, which is Bridget, and Z. Well, what is Z? Let's look for all the child with Bridget and Z. So, oh, there we go. There's a child with Bridget, and then Z must therefore equal Caroline. It's the only option that makes this work. So we've set Z equal to Caroline, and then that means we need to check descend. So and descend Z comma Y. Well, in this iteration, Z is Caroline, and Y is Donna. So we're going to check descend Caroline Donna. New iteration, right? So this is the recursiveness of this. We're going to check descend with Caroline and Donna. So the first thing we check then is this descend x comma y because it's first in our database. And so if Caroline is x and Donna is y, then x equals Caroline, y equals Donna. And so we check if child x comma y. So child Caroline Donna. Well, this is true. Yes. So we found this to be true, where this x is Caroline, this y is Donna. So we're going to pass all this information back up, pass all this information back up, and we said, all right, we found a path through all of these iterations that says that Anna and Donna are descendants. And this is how we got there. And so we get true first, because there's still a couple more things to test. And namely, we have to finish testing our last little descend check here. We tested with Caroline and Donna here. We have to check Caroline and Donna here. And this will end up being false. This will not work because there's no child that ends up working for this combination. So we get one more false afterwards. So this decision tree allows us to recursively find Anna and Donna are descendant, or Donna is a descendant of Anna. And if you follow it another iteration, you could find Emily also as a descendant. So this is our first example of recursive programming, and kind of following the decision tree down to see what happens. As a couple food for thought experiments, let's do a couple things. If I switch the order here and run, I get a similar result. This is fine. If you check the decision trees and follow through, you'll see that this works and this is completely fine. But my question now is, and this is an interesting little food for thought experiment. Uh-oh. If we put descend z comma y first here, we have a stack limit exceed. This is an infinite recursive loop, right? Because the first time, if we look at this, the first descend we check is x and y, and that checks a descend with z and y, but there's no restrictions on what z is. And so there's a lot of combinations we could try. And so basically what ends up happening is we are infinitely going to call descend. Because descend is first in the list, we're going to call it over and over and over and over again without any restriction. And so we'll run out of memory. And so this is what I wanted to highlight, is that order matters. And then even if so when you switch the order here, we get true the first time. And then as we continue, we run into a similar problem where we go infinite again. Now I'll leave you as a thought experiment to run through the descend trees here. If I get a request, if you don't understand this, and you'd like another video to explain this particular scenario, please send me an email. I'll be happy to run through it and describe it. But I think it's a good thought experiment to see why we find true, but then also go infinite. So following this branching path, iterations down the descend path, I think hopefully you'll be able to find this, but what I want to warn is order matters in Prolog, and it actually just follows through it checks every possible combination of whatever thing you're checking all the way through. So be careful about how you order these. Usually if you're going to make a recursive call, you want it to be at the very end of your statement if possible. You would like it to be the last thing that's evaluated, so that all the other conditions have to be met first before you go recursively call things again. That's just a good rule of thumb that when possible, put your recursive call at the end to avoid this infinite stack problem. So hopefully that makes sense. This is a really tricky video. It's a tricky concept. So if you need if you have any trouble, please let me know. I'll try to make another video to go over more recursion if you need it. Hopefully that all makes sense, and let me know if you have questions.